Testing.
Thank you so much.
Oh, you need a presentation, don't you?
Yeah, probably. We'll wing it. All right, so we are Team Hyperion from LSU, and our payload is apparently renamed Alamo.
I'm Joshua Collins, and I'm the electrical section leader.
Hi, I'm Victor Fernandez Kim. I'm the mechanical section leader.
Hi, I'm Steve Ward. I'm the first section leader.
I'm Adam Winston, and I'm the assistant project manager.
Hi, I'm John Azenwa, and I'm the electrical and mechanical liaison. I'm Brian Stutzman, and I'm the project manager.
And I'm James Villian, and I'm the procurement manager.
The goal of Indra ionization nexus for discharge research in the atmosphere experiment is to measure the breakdown voltage of the atmosphere and recreate Paschen's curve. Paschen's curve is the law governing electrical breakdown voltage in the atmosphere. It was made up by a man called Frederick Paschen when he did the experiment at different pressures to make the curve to find the breakdown voltage in the atmosphere using two spheres as his electrodes. Our science objectives are to observe the breakdown voltage in the atmosphere over the range of the balloon flight, and to record the breakdown voltage in the atmosphere to recreate Paschen's curve with a 66% confidence.
These are expected results. We got these. These are expected results. These results are to recreate Paschen's curve within 66%. We got these by testing in a pressure vacuum chamber to get the correct error bars and data points needed for the flight.
Our technical objectives is to meet all the requirements set forth by our ACES management staff. And we also had, since we're dealing with high voltage, we want to not interfere with any of y'all's payloads or any other payloads. And we shall have data recording system, i.e. a balloon stat or circuit boards, to record the data while we're on our entire flight and to be able to recover that data and analyze it once we land and recover.
So this is a high-level schematic of our payload. Basically, we have a power subsystem that's powering three major subsystems. We have the balloon stat, which features the basic stamp processing and ADC. We have a sensor subsystem, which is our pressure, temperature, humidity, voltage, current, things like that. And we have a spark generation subsystem, which is responsible for turning our raw battery voltage into high voltage and applying it across the spark gap.
All right, we'll be going into talk about our payload design. First things first, we'll talk about the balloon stat real quick. For the balloon stat, we have a basic stamp here, which is a real-time processor, and then we have a 4-channel ADC channel, a 4-channel ADC, and we have a voltage regulator that maintains the voltage of the balloon stat at 9 volts. There are connectors for interfacing with other boards. Next, we have. So this is this was called the Weeby board. It was designed by LISC staff, and it has pressure, temperature, and humidity sensors on it. The pressure sensor is going to be able to go all the way from 0 to 130 millibar. Our humidity sensor is going to be able to go 0 to 100% relative humidity, and our temperature sensor is going to be able to go from about 40 degrees Celsius down to about negative 90 degrees Celsius. So it's more than enough for our expected range for flight. And this is how we'll be able to get our 4,000 volts for our scientific experiment. We have a high voltage DC to DC converter that is controlled by a digital to analog converter that will supply the 4,000 volts. And then we have a detection system built in place to detect whenever there is a spark that occurs. And we are also recording the voltage directly off of the DC to DC converter. How we accomplish this for the arc detection is we have the current monitor pin of there's a current pin of the HVDC, which we amplify that toward, can't see it right here, but it's a gain of 5. It's compared to a variable voltage from another digital to analog converter, and that it's compared, and whenever the current exceeds a certain threshold, a spark is considered to be detected, and it toggles a B flip-flop to register that there has been a spark that occurs. And here is our board that we have for the arc detection system. You have our power supply for the HVDC control, and then we have our chips here for all of our systems.
So with that in place, we could find out or start beginning on working on the spark gap design. We first started off with a pointed plane, and then we wanted to try out a wire cylinder because there was some evidence in past research that wire cylinder is more consistent sparking. So we tried that in a test, and we found that wire cylinder is not as effective, and it takes a lot more voltage to actually get a spark. So we reverted back to the pointed plane. So here you can see. How do you do this? Here you can see the point, and we just use a nickel cadmium soldering tip and an aluminum plane. And this is going to be gripped down with just some screws, and these are two. This material and this material are actually made of epoxy potting material. So it would be insulating the high voltage on either side of it, and there would be no current running through the middle of the body, which will be covered later on. So through this side would have the positive voltage, and this is the negative voltage, and the current would just run through, and it would spark through here.
So this is our power budget. On the far left side, those are the individual components of the system. Perhaps the most important thing is the measured current that each of the components is going to draw. And then you factor that in with the duty cycle that each component is going to be operating. For the most part, the components are going to be running the entire flight. The basic stamp, all that's going to be running the entire time. However, the HVDC has two different cycles, when it's ramping up the voltage and when it's sparking, and when it's not doing anything. So those duty cycles are different. When you factor that in, we come out with a total needed milliamp hours of 447.92. Which, using 8 AAA Energizer lithium batteries, more than meets this power requirement for our payload. So this is an internal shot of our payload. At the top, we have our 3 boards. The very top board is the Weeby sensor board. The middle one is the balloon stat, and the one on the bottom is the arc control and detection board. Down on the bottom, we have our batteries, and underneath that is a foam holding tray that the HVDC and spark gap are held in. If you want to go to the next slide. This is what that foam block looks like. We took a mold, filled it with great stuff, insulating foam, and then carved out the necessary parts for the high voltage converter, which is on the right, and the spark gap, which is on the left. You might notice that the high voltage converter has a huge block of black stuff above it. That's high voltage potting compound, which John will go into here right now.
Okay, so the high voltage potting compound, we used an epoxy resin. We chose this pretty much because, for one, it's not exothermic. So some of the other ones we tried, gave off a lot of heat, but this one didn't. And so it also has high work life, and it doesn't corrode the copper, and it's not chemically reactive with any of the things on our spark gap. Also, it pretty much doesn't allow a spark to go across the pins because we did a test with some prototypes. We made prototype HVDCs out of foam, and we realized that if we run high voltage through the input wires, there's a spark across, and so this doesn't let the spark go through.
Right, so as you guys saw in the past pictures, this is the design that we went with. You can see in the middle is the composite wall that would be separating the high voltage materials and the electronic boards. So on the one side is the electronic boards, and then I'll have the three Weeby sensor or the Weeby, the control electronics, and the balloon set. And in the other one is the foam, great stuff, the dielectric insulator. The overall dimensions are around 16 by 21 by 21. That is all compact. There's two holes on the top and through all the way down, 17 centimeters apart, so we can interact with the balloon.
Alright, so this is our weight budget. As you can see, the most important stuff that you can take from it is that it's over 500 grams. We're at about 600 grams right now. But that comes from pretty much just having a lot of circuitry that has to be interfaced to make this spark gap, or to make the spark and to have a working payload. Also, a lot of the weight comes from the foam block itself. And we also had some problems recently that we had to deal with and add about 50 extra grams. That had to do with a ferrite little piece, which is about 25 grams, and also a larger ground plane. So.
Okay, you guys got 5 minutes.
For design, first, the software data format. The software data format is basically a calculation of how much each type of data will need to be. Each one is at 1 byte. We'll be taking 8-byte events at each data point. We'll be taking a data point every 30 seconds, and the flight will run for 185 minutes. This builds 370 data points. This uses less than half of the EEPROM's memory.
Okay, the pre-flight software is generally just to get rid of all the data values that are stored on the EEPROM that may have been there as a result of testing, just to make sure we have enough memory to store all the data events that we will collect during our flight. And it initializes the first address that we want to save data values to, in case there's something we have previously saved on the EEPROM that we would like to keep. And last, it sets the real-time clock before post-flight or before flight software is run.
The flight software runs in a modulated process, first checking to see if we are on the ground. The flight software does not actually work until we get up to about 2,000 feet. It begins by setting the DAC to 0, which resets the HVDC back down to 0, moves on and actually starts ramping the HVDC up, constantly checking to see if there was a spark. If a spark is detected, it takes a data point, taking all the environmental values, and then writes all of these values from the environment and the spark gap to an event in the EEPROM, and then it checks to see if the EEPROM is full and runs back to begin the loop again.
The post-flight software is generally just to display our data back to the debug terminal so that we can use it for analysis later on. It just reads each event and separates each value, each sensor value by a comma, and we'll take those values and use them in our ground software. Our ground software, what we do is we take the debug terminal, we copy the values from the screen, and we're able to put that in a text file, which can be imported into Microsoft Excel. And Excel has a function that allows the data values separated by commas to actually become columns, and we can just take that data, apply all of our conversions, and create our science products from there.
All right, so as Dr. Guzik mentioned, there's I guess a possibility of rain tomorrow. We're also concerned about condensation in and on the payload through flight. So we did what we called the spark gap wetness test, where we basically just soaked the spark gap and saw if it had problems. This was our first gen, which had wooden end caps. We ended up replacing those with epoxy, and with the epoxy, we basically had to sort of submerge the spark gap in a puddle of water before it would actually have a problem. So we're fairly confident that even if the spark gap gets wet during flight, that we're not going to see any dangerous side effects. We also had a concern that the sparking, it emits a lot of radio noise interference, and we were concerned that that spark could affect the radio locator beacons or the cut-down mechanism for the balloon. So we put a spark gap in a chamber. We ran it for 10 full minutes of just constant arcing right next to the beacon and the cut-down mechanism. and neither the beacon nor the cut-down mechanism were interfered with, so we're fairly confident that we'll be fine for flight. So next point. So, finally, the current state of our payload. While we were integrating the payload, we had an issue where every time we would spark, basically the basic stamp would just stop working. And so what we ended up doing is we put a bunch of filter caps on the power supplies, added a massive ground plane, and added a ferrite core to the HVDC control feedback wires. Through all of this process, after doing all of that, we were able to get just like 10 full minutes of just constant arcing and sparking, and there were no ill effects to the basic stamp. So at this point, we believe we're ready for flight. So, any questions?
Very good. Were those, that was all measured weights in your current configuration of your ferrite core and everything else?
All those weights were measured except the copper plane, the extra grounding plane. We estimated it to be about 20 grams. Let me say it again. Okay, all of those weights were all measured weights, including the ferrite core, except for the extra ground plane that we added. We estimated that to be 20 grams because it was roughly the same weight as the ferrite core.
So how are you going to lose 120 grams?
I don't know.
Okay, we'll have to talk about that.
Okay.
Anything else? Michael? Okay, very good.
That's okay. I should have enough.
Forward, back, and this is forward, back, like that. We can.
Alright guys, we're UNO, Team Icarus. We're doing a total atmospheric radiation except for visible light. Basically, we have Brit, which is our,
I'm Brit Aguda. I'm in charge of the ionizing radiation portion of the experiment. Right here we have William Lesh. He's actually the project leader for the UV experiment. We have Michael Flott, who's actually he's our chief electronics and software engineer, and we have Paul Fuller, who is our chief mechanical design. We also have two other team members who are unable to be with us today, in which case it's Harris Lamb and Ahmed. Unfortunately, they had other things they had to attend to. All right, for the mission.
Alright guys, so like I said earlier, our mission is to measure total atmospheric radiation. And our objective is to come down with all of the information to be presented. And then we have a few things we would like to add on top of the cake. But that's basically, we saw that, especially with UV, we had a high failure rate. So anything we actually wanted to do with it after that, we actually just wanted to make sure we could get the data. After our radiation, the atmospheric radiation, not the UV, has a cosmic radiation background applications, and that's obtained through counts per minute. Okay, so our basic mission goals were to make sure that the flight goes up 100,000 feet. Pretty basic to everybody. The next one is that we could measure in all bands, UVA, UV, UVC. Now all of these bands, I'll go through that in just a moment. We also needed to accurately measure without too much interference the cosmic radiation through Geiger tubes and a, what is it, bandwidth?
On the spectral energy bandwidth.
Energy bandwidth, I'm sorry. We have a few backup systems to monitor and make sure that we don't go over too much with temperature, and that if anything shuts down, we can monitor and see where that temperature rose beyond the operating capacity of the circuits. And then we have computational engines for when we get back to the ground to analyze the data. Now, this is our basic scientific background about UV. It's that UV is broken down into the three groups, like I said earlier: UVA, UVB, and UVC. UVA, which is going to be 400 to 300 nanometers on the wavelength. UVB, which is 400 to 320 nanometers. UVB is 320 nanometers to 280 nanometers, and UVC is going to be that 280 to 200 range. We don't actually expect to see any of the UVC since it gets filtered out pretty high up there. But the UVB and the UVA both reach the ground, but we do get some filtering from the UVB. So we're using basically our UVA as a reference for everything, since we can see, even on the ground, most of the UVA. UVB, on the other hand, we're going to measure that, and if we get UVC, that will be cherry on top. Now,
all right, for the ionizing radiation portion of the experiment, all right, first off, we have to go ahead and take a look at what radiation is. Radiation is going to be highly energized particles moving through free space. There are many different types of radiation. The three most common ones that we deal with is going to be alpha radiation, beta, and gamma radiation. Alpha radiation is going to be basically the product of alpha decay. It's going to be helium-4 nuclei. Usually the most common example of this would be uranium decay. You can see up here. Beta radiation is going to be positron and electron emissions. Basically, it's just going to be free-floating electrons. This is mostly put off by various nuclear processes. The last and most common is going to be gamma radiation. Gamma radiation is going to essentially be high-energy photons or electromagnetic waves at a very, very low or very, very short wavelength. The gamma radiation comes from, once again, a plethora of sources. Mostly in the atmosphere, we're looking at sources from extraterrestrial cosmic waves, but we also have on the ground, we have a large amount of terrestrial radiation coming from the soil, from trace amounts of radon. What we're going to be measuring is we're going to look for the equivalent dose in the atmosphere. A lot of past teams have just came back with the radiation rate, the encounter rate, which is in counts per minute. We're going to go ahead and go the extra mile and say how much would be absorbed by tissue if a person was up there. This is actually very, very useful for most avionics, most intercontinental flights. They're exposed to a lot of radiation at high altitudes. And the overexposure to such radiation can cause burning, tissue damage, burning, illness, even death. All right.
This is a diagram of our entire system. We had two control systems, one for the ionizing radiation, which is C1, and the other side is for the UV. If you look, the P is the power. We just basically use two 9-volt LiPo batteries, and basically the sensors are temp sensors. We have one for each. We had two for each one. Internal temp of the Arduino board and external temp. One was to measure the resistivity of our actual sensors as a function of temperature. We actually have for our UV. We actually added a 16-bit A to D to get higher resolution, which is C8, and they just send out. They just get data from the sensors down here and send it to the Arduino. For the ionizing radiation, we also use two Arduino Nanos in I2C protocol to communicate as well. So we'll get more into that later. The system design, we basically used ultraviolet sensor package, one for each corresponding band. These diodes were mounted in a custom-built 3D printed holder, which we actually have some to pass around later. We use the Arduino controller as our main brain, and op-amp circuits to control the voltage, to convert the current from the sensors to voltage. Also to control our gain as well. The gains were calibrated using the Langley method to estimate the maximum voltage we would reach above the ozone layer, and to avoid saturating our sensors. And we also sampled at high rates to account for data aliasing as well.
All right, for the ionizing radiation portion of the experiment, I went ahead and I designed what I call the ionizing radiation identifying system, or IRIS for short. It's basically a system that's designed to pick out the types of, to determine the effective dose of radiation, as well as try to get an approximation on the spectral bands of the radiation. The system itself is going to use two main sensors, the first of which is going to be an RM60X2 by Aware Electronics. It's going to be a Geiger-Muller. It's not an actual counter, it's just a sensor and a transducing circuit. The second sensor is going to be an RG2007, which is a PIN array it's a PIN diode array. It's basically just an array of photodiodes tuned to different energy levels of ionizing particles. All right. We use 3 microcontrollers for the IRIS, in which case the microcontrollers are going to control the whole system, communicate in between themselves, and compare the data. Here we have a little comparison between the Arduino Uno and a basic stamp board, in which case you can see the cost-wise it's a lot better, lighter weight, and better computational power. And a lot of people use the basic stamp. Think about the Arduino next year. I set up a custom design circuit. I set up a custom design circuit to interface the sensors to the main CPU. The main CPU is going to basically use an I2C protocol. We'll get more into that later. And once again, the main CPU is going to be an Arduino R3 Uno with an Adafruit data logging shield attached to it. Okay, now we'll get into electronics.
So for the UV sensor package, we basically we have an onboard SD data logger. We basically use 2, one for each project. The UV sensors are connected to the Adafruit 16-bit A to D, so that we can get a more accurate measurement than the onboard A to D, which is 10 bits on the Arduino. The photodiodes basically output an analog current, and we convert that into a voltage, which is we got a preamp here conditioning the circuit, and then we have a butterworth filter, which is basically a low-pass filter to cancel out noise, so that we can just basically get the data that we want. The negative feedback circuits for each sensor, like we said, were determined by using the Langley method.
All right, for the ionizing radiation portion, for the IRIS, we have a system diagram showing the main 3 functional groups of the system, in which case it's divided up into a CPU, or centralized processing unit, NRD07 and NRD60, which are just names that I came up with to just kind of do shorthand. Now the whole system is going to communicate using an I2C protocol. As you can see, the CPU hooks directly to a lithium-ion 9-volt battery, and it distributes power to the other sensors in the system. It's all powered by a LA552 Energizer advanced lithium battery. The CPU for the IRIS consists of an Arduino Uno R3 outfitted with a data logger shield. The data logger shield itself is actually very, very useful because it comes with an RTC and an SD card interface built in. So it kind of saves a lot of the hassle work of dealing with EEPROMs, because then now you get to just put it on an SD card. The memory, it communicates with the it communicates with the RTC and the sensors over the I2C, but the memory to the SD card is covered by SPI protocol. This is most.
You got 3 minutes
3
left.
minutes, gotcha. All right. Electrical design for the sensor interface. I designed a circuit to interface the sensors with it over the I2C bus, in which case we have a transducing circuit. The circuit is designed to work with either sensor interchangeably. Here we have a picture of the sensors. Up here we have the Geiger tubes. I encased them in foam for protection, and we also see the PIN diode array. This is a picture of the whole system taken apart. This case is the data logging shield, the Arduino, the two Arduinos, and the Geiger Muller tube.
The software for the UV project is as follows. Basically, we sample 5 times a second. We use the high rate of sampling to account for the spin of the box and other other ways that the data can be corrupted. But the code basically initializes the conditions, and it just basically polls the sensors, each sensor, and saves the data every 200 milliseconds. And then we track the internal and external temperature and save it to a 4 gig SD card, so that we don't have to really worry about filling our memory up.
All right, for the Iris, the Iris uses 3 different microcontrollers, each programmed with their own software. The CPU is going to be programmed with a very simple, basic program where it's just going to go through, query all the sensors, and save the data, and repeat itself. It's going to do this once a minute. For the sensors, for the Arduinos,
1 minute.
1 minute. It's going to flow through. It's going to count the pulses on an I2C query event. It's going to go ahead and go through. The second one's going to be very similar. For mechanical design.
Keep clicking. Mechanical design, it's from insulation foam, 3/4 thickness. That's our exterior. We also created a 3D printed lens holder. Went through a few different examples on that one. We cut the side of it in order to angle it at the optimum angle for the sun, as well as our interior is layered with low density foam wrapped around by Mylar insulation. Next, we went on to testing. We have our cold testing with inside the payload, as well as cold testing on the sensor, since they will be outside at the elements. We even froze them down with frost and got less than 10% discrepancy in voltage. We also did spin tests in order to determine what signals we will get as the payload is spinning, as well as a hot test, and also a drop test in order to make sure that the payload will survive a 1-story drop.
Any questions?
All right, good.
Wait, we're at 407.
407. Okay.
I have a question.
Yep.
Your data logging shield, did you build that or is that all?
No, you can buy that from Adafruit.
The Adafruit company, and I highly recommend it.
It comes with an onboard real-time clock, and so, yeah, and as long as you have like a little watch battery in it, it keeps ticking.
And is that connected to the nano?
Yes.
Well, it's actually to the Uno it connects to.
Yes.
Any other questions?
Any questions?
All right, thank you very much.
All right, thank you. All right. Okay. Okay. for it.
We're here presenting from Loyola University.
Use the microphone.
Hi. It doesn't work. Is it on? Hello? Is it?
It works.
Okay. Well, we're here from Loyola University. I'm William Dewey. This is Thomas Black. This is Riley Mays, and Cameron McCormick. And we will be presenting on research that we've been doing on optimizing a Gerdie condenser, and I'm going to go into what that means exactly and what our objectives and our intentions were with this project. Well, our mission goal is to measure the atmospheric ion concentration up to 100,000 feet in relation to the specifications laid down by LA ACES, as well as optimizing older previous designs of Gerdie condensers in order to delegate appropriate weight so that we get our weight below 500 grams for this project. We almost managed to get there. So what we're trying to do is we're trying to measure what the voltage across our capacitor plates are going to be as we ascend up to 100,000 feet. And the requirements is that we meet the payload weight requirements of, we go right here. Improved design of the payload that will allow us to measure the ion concentration between our capacitors. So basically, we're going to be charging up two capacitor plates, one to a positive voltage and one to a negative voltage, and then removing the power supply and watching how quickly these plates decay. And assuming that there are concentrations of ions in the atmosphere around our plates, these concentrations would expedite this decay. So that as we ascend through the atmosphere, we should see varying decay rates as we remove our power supply from our Gerdie condenser. And the ions actually come into the upper layers of the atmosphere via a lot of different mechanisms, and into the lower layers of the atmosphere via different mechanisms involving geophysical ions, which are produced from the soil, and aerosols in the lower layers of the atmosphere. And in the upper layers of the atmosphere, things like cosmic rays and cosmic interactions and nuclear reactions in the upper layers of the atmosphere produce these ions. And the positive plate on our board will detect the presence of negative ions, which will carry the charge away, and vice versa for the negative charge.
So as Dewey alluded to, our measurement apparatus to detect the ions is basically just a giant capacitor. It's a cylindrical capacitor as opposed to parallel plates. Actually, outside of it is a Faraday shield to minimize any interference we have. And how it works is as ions flow in between, they interact with the electric field and they experience a force. And so that is the charge that gets transferred between them. We disconnect it, we charge the capacitor, disconnect it, and the voltage will decay. And the only way it can decay, if it's not connected to anything else, is through this charge transfer via the ions. It's kind of like why distilled water doesn't conduct electricity, but salt water does. It's the same idea. You have these ions as the charge carriers. And so then once we have the voltage decay, we can fit it to a best fit curve, exponential decay, and using that function, we can find the time constant. From the time constant, we can use these equations to back out the conductivity of the air that's passing through our capacitor. We have been working off of some previous iterations that LSU has gone through, and we're very thankful to them for helping us along the way, fixing some problems we ran into. This is one of the previous payloads that went up, and this is what we're trying to improve upon. How we did that is they determined through previous iterations that the caps on the top and bottom should be Teflon. They used plastic, but even that was not insulative enough, and so Teflon is much better. Additionally, we shaved down the amount of Teflon used because Teflon is very heavy. We used slightly less material for the capacitor itself, again to cut down on weight, and it was determined that 30 volts would be a good voltage to detect a significant number of ions in the atmosphere.
Hi. So here's our block diagram of our circuit. We have our systems integrated through the balloon sat board.
which connects to our Gerdie control system and subsequently to our condenser. Okay. And then that was it. Okay. So this is our Gerdie control circuit, and it consists of primarily three components: our input circuitry, our signal conditioning, and our switching circuit for switching our condenser on and off. And so we start coming in, and our input circuitry consists of a low leakage operational amplifier, which acts as a buffer at that LM6042, and two JFETs allow the switch to reset. We anticipate, depending on the op amp, but typically between 5 and as high as 20, but on average 10 amps of leakage. At 8 femtoamps, we anticipate approximately a 10% error in measurement. So it's fairly adequate.
Our voltage divider and our signal.
In our signal conditioning, I'm sorry. Yeah, that might work. It's weird. Okay.
So we have our voltage divider to reduce our voltage input from our balloon stat board on the way in as our signal conditioning. And it's then
face the audience.
And
talk this way. Don't talk to the board. Talk to the audience. There you go.
So anyway, so it switches through a JFET interface, and it's no calibration necessary. It's done afterwards. And modified the switching interface to make it more simplified and therefore hopefully better. This is a test, an initial test run on it. As you can see, experience a exponential voltage decay from a 25 volt charge, and we fit that to an exponential decay curve.
Okay, so our fluid box was designed so that the experiment and the box itself would sustain and perform under certain conditions, those being a temperature range from negative 70 to 30 degrees Celsius, a pressure range from 6 to 760 torr, and a drop at terminal velocity about 6 meters per second. In order to do that, we constructed it out of that urethane foam and wrapped it in. Hello? Okay. And wrapped it in aluminized mylar. As you can tell, there are two separate sections of the box. The one in the back being where the condenser is. That has to be open to the elements so that laminar airflow over the condenser itself can be achieved. And then the electronics are in the front portion of it, and that is obviously not exposed to the elements. Our weight budget, as you can see, our condenser is almost half of the allotted weight, so we did go over by about 115 grams, which we are borrowing from our other team at Loyola, who, this is a teaser for the next one, but are under by 121.6 grams.
Okay, so for the flight program, basically we just slightly modified our program from a previous experiment 2 years ago. Now for that, we first we initialize the clock. We get a timestamp, we then write that timestamp to the real-time clock. And the flight program is where it gets a little bit tricky. That's where we actually had to spend the most amount of time and do the most amount of work to actually read this decay, or I guess potential. So basically we worked on that, we got some values, we tested it, and then we get this post-flight software. Now the post-flight software now logs the values, and then we use term 232 to then import it into Excel, in which we extract the data and produce plots of hopefully good voltage decay once we actually send this balloon into the atmosphere. Okay.
You got about 4 minutes left.
Okay, and so the data acquisition part, which I hadn't talked about before, basically we're taking one measurement every 2 minutes, and then from that measurement, it's about 240 bits. So we're estimating the total flight time to be about 85 minutes, and at that point, we're then, that gives us about a 10,200 bit limit. And our span is from 0 to 30 volts. Okay, so our team management was distributed evenly among everyone. We each took part in successfully completing our duties and responsibilities. Some of us worked on more than one part to reduce the workload and hopefully accomplish our goal when we send our balloon into the atmosphere. And we would also like to acknowledge NASA as well as the ACES program, and of course the Loyola Department of Physics and Dr. Patrick Gerdie for providing us all the needed resources for this experiment to work. Thank you.
So did I mention to you guys that in fact what we do is we have this little competition. It's called competition by fire with the two heaviest payloads that show up in FRR. They get to fight it out in the parking lot here to decide who is actually going to fly and who isn't. So, as soon as one of the other team is dead, then the other one is. It could be just like one guy left from the other team, and So, how are you guys going to lose weight?
We're gonna borrow weight from our other team who's.
No, that's not what I asked. I didn't ask you if you were going to borrow weight. I asked you how you're going to lose weight.
Nutrisystem. In the future.
So what is it that you can remove from your payload to reduce weight?
We can use lighter weight materials, the Teflon.
Today, this afternoon, before 6 p.m.
Oh, yeah. We stripped it down to the bare.
In the future, we could optimize our design by going with a different size capacitor and reducing the dimensions of the cylinders. We could opt for thinner layers of Teflon. We could opt for thinner layers of our insulation foam on the box. But at this point, it would be really hard for us to cut the layers.
All right. Okay, any other questions? All right, very good. All right. Who's got the clicker? Who's got the pointer?
Hello. Good morning, everybody. My name is Sarah Lockwood, and I dealt with mainly the balloon stat as well as the FRR documentation of our project.
My name is John White. I dealt with software design and wire fabrication of the sensor interface board.
My name's Daniel Perez Alonso, and I deal with the wire fabrication and the mechanical design.
And my name is Cara Turley, and I dealt with the mechanical design and with the balloon set. We're missing the fifth member of our team today due to medical reasons, but his name is Antonio Araya, and he's the national project director.
The same batteries.
Our mission goal is to investigate the layer of the atmospheric using an instrumented sounding balloon and to collect and analyze data on atmospheric temperature, pressure, and humidity as a function of altitude. Our science goals and requirements were to gather data on the atmospheric temperature, pressure, and humidity, and to determine the approximate altitude of the tropopause. Our requirements were to design and implementary circuitry and sensors to measure these atmospheric temperatures and calibrate sensors to obtain accurate measurements. Our technical goals were around the same: to build an operational payload that can endure conditions of balloon flight, and to determine where and if the payload flies through a cloud. Our requirements were to design circuitry and payload to operate under flight conditions and record data as a function of altitude.
Right. Our atmosphere has four main layers, starting with the troposphere in the bottom, then the stratosphere, mesosphere, and thermosphere. For this experiment, we're only going up 100,000 feet, so we're getting to the stratosphere. The temperature in the troposphere, which is the lowest layer, starts at the temperature we're today and goes up to negative 52 degrees. And then when it enters the stratosphere, the temperature starts rising to approximately negative 3 degrees. And for pressure, we're going to start with 1,000 millibars approximately, which is the pressure in ground level, and it will go up to 1 millibar in the stratosphere. Sorry, and the humidity will vary depending on the weather of the day. So.
And this is our payload box that we designed, and our balloon sat is right there next to our batteries. The top circuit board is our sensor interface, and the bottom one is our balloon sat. The top one, the sensor interface, takes in all the data, and the bottom, the balloon sat, is processes it and acts as the sort of brain of the whole thing. So our payload diagram, it has two systems. It has the mechanical support system and the thermal support system. And the thermal support system is passive. That basically means that it does not have a heater. It just relies on the material it relies on the material of the box. And it's also shock absorbent, and yes, and this is a mechanical diagram, the dimensions of the payload box and the measurements of the material we use to construct it. The white part at the top is where the circuit boards go, and the partition separates the batteries from it. And
so this is the schematic of our sensor input board. As you can see, we have the basic stamp which holds about 16 kilobytes worth of memory. We're going to be taking input data about one time every 5 seconds. We have the analog to digital converter, which will give our atmospheric pressure readings, our temperature readings, and our humidity readings, convert them to an 80s screen, and then we can then plot it on Excel and we get our graphs. Next slide, please. This is our power budget. We have a total of 1,400 milliamp hours. We have 2 batteries that are going to give us a total of 80 milliamps to the balloon stat circuit board on the bottom and 25.4 milliamps on the interface board over the course of 3 hours during the flight. Total amplitude for amp is going to be 105 milliamps. We have 240 milliamp hours for the balloon stat, 75 milliamp hours for the interface, for a total of 315 milliamp hours. And over the course of the flight, we'll be putting out 12 volts of power. Daniel?
For a weight budget, the balloon stat board weighted 74.2 grams. These are all measured values. The sensor interface weighted 104.5 grams. The 2 6-volt batteries weighted for a total of 84.5. The payload structure weighted 115.4, and we have a total of 378.6 grams. That means there's about 121.4 grams free.
So we have 3 diagrams for each sensor. The schematics for our interface board, we're going to be able to collect data readings from a silicone diode. We get a potential difference of about 0.0022 volts for every 1 degree plus change. Can you go back one? 1 in 457 transistor is going to give approximately 0.8 volts at our lowest temperature, which is going to be negative 80 degrees Celsius, and approximately 0.5 volts at a maximum 30 degrees Celsius. This is our pressure interface. We're going to be recording with just your normal pressure sensor. We have a resistor 4 and 5 are matched in a pair, as well as resistors 8 and 7 and 9 respectively. That's about it for that point. And finally, our humidity sensor interface. We just have your average humidity sensor that was provided for us by the program. And we'll have a potential difference of 0.83 volts at 0% relative humidity and approximately 3.98 at 100% relative humidity.
So we put our payload box through a series of tests, and the first 2 tests were the shock test procedure, where we basically just dropped it from 3 meters onto the floor to see if it would take any damage. And the second one was the thermal testing, and we just put it in like a negative 80 freezer and left it in there for 38 minutes to see how it would do in cold weather.
This is our vacuum test procedure to measure pressure that it will withstand in the atmosphere. We would power up the payload, run pre-flight software, run the flight software, place our balloon stat in the payload box, place our payload under a large bell jar, which you can see in the picture, evacuate slowly to 10 millimeter, and equalize pressure and remove the payload from the bell jar.
Right. For our vibration test, we attached a large spring of 1 Newton to support in front of a discharge side of fan. Then we attach the payload to the spring and turn the fan on to simulate the movement it would go during the flight. And after 160 minutes of the test, we take it out and give the readings.
In conclusion, our testing went well. Unfortunately, due to miscommunication with our programming advisors, we accidentally deleted the information, so we were not able to make our actual chart from the test, though we were able to successfully get readings and extract it. We made a minor error, which unfortunately cost us that data to make the graphs. But calibration and testing went as we planned and we are ready for flight.
Did you, before you deleted your data, did you actually look at your data from your testing? Yep. And so you had data throughout all your tests?
Yes.
Okay. And you now have these problems resolved as to how you're going to handle your software?
Everything's resolved. We're ready for
okay. All right. What else? Anything else? Okay, good.
Thank you.
Yep.
I don't know. You gotta turn it on. This is what the Ethernet is about? Yeah. Okay, let's switch. Here we go.
Okay.
So, alright, we're Team Galaxy from McNeese. I'm Mackenzie Hill. This is Taylor Williams, Ryan Swallow, and Chun-Li Zhao. Jonathan Garbo is not with us today. Taylor took over the computer programming. Ryan and Zhao had the electrical design, and Jonathan and myself took care of the mechanical design. Alright, so our goal for this project was to measure temperature, pressure, and relative humidity as the balloon ascends to 100,000 feet. Before we get to this, listen. Alright, the actual design of our payload here, we decided to go with, we did 3 layers of insulation, and we have 2 separate boxes. For the 2 boxes here, we decided to go with a staggered system. So this box here, this box here, we have the lid glued to the bottom of this box. So when we place this in here, have the lid of the outside box opposite the lid of the inside box to keep the heat trapped inside a little bit longer. We also have the inside box is a 1/2-inch layer, and the outside consists of a 3/4-inch layer and an extra 1/4-inch layer, which also gives us an extra lip for the lid to seal down better. And so here we have our so here we have our test for the mechanical design. We did an impact test. We put an egg in our practice box, and we dropped it from a height of around 5 meters. We measured the time and of course the height. And from that, we were able to calculate the acceleration and final velocity of the box. We read that the parachute is rated from 4 to 6 meters per second, and that our box could protect an egg at final velocities of 10 to 11 meters per second. So we concluded that the physical structure would be capable of protecting the board. Go ahead. The thermal test, we placed it in a negative 80 degrees Celsius freezer, and then we also had a Logger Pro temperature probe that we placed inside of our practice box and our testing box, and it was hooked up to a computer interface so that we could read the temperature, the internal temperature of the box as it changed relative to the external temperature of the negative 80 degree freezer. Go ahead. So this was our most productive test here. This was with 2 layers and with a hand warmer involved. We decided not to use the hand warmer. We'll talk about that later. But we started out at 32 degrees Celsius, and it took a little over 40 minutes to get to 0 degrees Celsius, which at that point our components would fail. And so this was with 2 layers, both of them 1/2-inch layers. So here we decided to kind of give us a safety buffer, and we put 3 layers
and we made the layers a little bit thicker. Go ahead. And then we will also have the temperature rising due to the just the actual board. And we did a test there. We put the board and we ran it for about an hour with the Logger Pro temperature sensor in there, and we saw that it raised about 8 degrees just from the board being placed in there by itself. For the last test we did a pressure test. We placed it into a glass container and dropped the pressure to a near vacuum. We noticed no changes, so we concluded that our box will withstand the low pressures of the high altitudes. Yeah.
Okay, I will talk about the electrical design, the power budget, and the calibration of the sensors. So, first, we have 3 sensors: the pressure sensor, the humidity sensor, and the temperature sensor. And the pressure sensor goes to ADC 0, the humidity sensor goes to ADC 2, and temperature sensor goes to ADC 1. And the ADC will convert the voltage to the digital signal. Then the microprocessor will store the data to the EEPROM. And also we have the real-time clock, which will set 8 seconds as a period. And when we get back, we will get the data from the EEPROM and do the data analysis. This is the power budget, and our total current is 74 milliamps, and the total power, our total current is 74 milliamps, and the total power is 820 milliwatts. Here is the power supply. We have 2 6-volt lithium batteries connected in series. The total is 12 volts. And 12 volts goes through the temperature sensor, the pressure sensor, and the balloon set. But the humidity sensor needs the voltage drop down to 5.5 volts. So we have a voltage regulator on the balloon set that will drop down the voltage to 5 volts. This is the temperature sensor's calibration. We use the RTD to do the calibration, and we also use the dry ice to drop down the temperature. The dry ice will lower down the temperature to negative 76 Celsius degree, and we use multimeter to measure the voltage for the temperature sensor. Then we note down the voltage of the temperature at negative 60, negative 50, negative 40, and 10 by 10 to 0, and also the temperature. Here is the data we got from for the temperature and the voltage, and we got the slope. The result is that slope is 2.07 millivolts per degree, and we got the data from the data sheet is 2.2 millivolts per degree, and due to the unstable temperature of RTD, the result is acceptable, and then we got the equations here. This is the pressure sensor's calibration. We use a pump with a pressure gauge, and we connect the pump to the pressure sensor by a pipe. Raise the voltage of the pressure sensor from multimeter while pumping the pump. This data we got for the pressure and temperature. The slope is negative 0.3 for volts per kilopound, and we get the equation between the voltage and temperature.
Along with the temperature and pressure test that we did, we also did not too much testing with humidity, because it turns out we didn't have too many devices at school that measured humidity all that well, and so we used values that we got from the Weather Channel, our local weather station, to get the humidity for that day, and compared it to the voltages that were expected here in this table. This expected values come from our data sheet. So our calculations are, I think they were 0.02 off from this, and we can change that using the resistors on board of the sensor interface module to change the gain of the going into the ADC. One of the things that was kind of an issue for us, because we needed to do it as simply as possible, was the placement of our sensors. We ended up in the end deciding to run it out of the bottom of the box and just having a wire that connects to the sensor interface board. So we left about 4 inches of slack coming out of the bottom of the box so that we had room to move them around and so that they less likely to get damaged. One of the other concerns that we had was having a hole at all in the box. So we insulated it at first with window caulk, and window caulk was too soft and it came out too easily. So we used a silicone gel that hardened and that helped a lot better. We originally were going to use a hand warmer, but we were discouraged to use that. We understood the cost of using it, but the reason we were going to use it was to give us a better shield of heat inside the box, because that's one of our main concerns. We need to make sure that the box does not drop below 0 degrees Celsius, because the ADC, the microcontroller, and the humidity sensor, no, one of the other components don't stop working at that temperature. We replaced not replaced, but we took out the hand warmer and used the Econokai skin, the heat shrink skin, to better hold in the heat that we will be starting off with. And pass it over to Taylor.
Yeah, you got 5 minutes.
Okay, that's plenty of time. All right, let's see. Here we go. All right, so I just handled the software. So from the ADC on is kind of my job to take care of. So we have 8K of the EEPROM that we can store data to. So for our in-flight software, we're going to go through and take samples from our 3 sensors every 8 seconds along with a timestamp. That'll give us a little 6-byte packet to work with. And with 8K, we can get about 1,350 packets. So we'll fill up all but 96 bytes of our memory. So we figured that would probably work and give us enough data to work with over the 3-hour flight. So when we power up the board, we have a hardware switch that is a program select. If it's high, then we'll actually be reading from the sensors, and if it's low, we're going to be pulling out from the EEPROM and reading our data off. So once we've read our data off, we need to convert all of our voltages to scientific values that are actually usable. So we're going to use a 4-point interpolation for that, and we're going to just convert seconds to total seconds, hours, minutes, and seconds to total seconds. That's fairly straightforward, so I didn't put anything about that up there. Not too hard to do. The final thing we're going to do is we have a little script program that's written up in Bash. It's going to actually do the conversion for us and then call a QXFine interpolating program that'll take in our data as 3 separate files for temperature, pressure, and humidity, and also the altitude data, and interpolate them over time. It's going to interpolate and get 5,000 points, and then we can graph parametrically each of our data points against altitude, and we're going to do that using NuPlot, and then that'll put out our graphs. They'll be saved, and we can take a look at what that data looks like once all that's done. And at that point, that's everything we have. Is there another slide? That's it. All right, and that's all we have. So, do you have any questions for us?
What's your weight?
45.
45 grams?
485.
485.
That was our weight. That's our weight, yes.
Okay. Let me see your box here. Okay. So you're just going to pass a string straight through the interior of your box?
We had string through it already.
Probably got strings for braided. Braided. They only be against the exteriors, so the string would be run through it. Yeah. So it runs between the second layer and the box that the actual board goes in. We're never gonna get this straight through that.
Are the strings thick or something?
It's just that they have to be run through. It's not. That wouldn't be easy. It's not gonna be easy.
Well, could we run the strings through it, then assemble it?
We might be able to do that.
Because we've run these strings through it.
That was the plan. Was to
run the strings through
and then put that inside. Right.
Then your strings probably it's kind of squished up against the sides. I imagine it's not very.
You're gonna have to chop out the section out of here.
No big deal. That would be pretty.
Okay.
Those strings are you're gonna have to get a D-size screw in there.
Okay.
Maybe we get some saws and maybe that will go inside.
Okay. Rating 5, you said? Yes. Any other concerns? What's that toggle? We're using a toggle to make sure that when we start it back up, it doesn't overwrite our data, so that we're able to pull off the data that we have collected previously. Because what we were understanding that if we start it back on, the program's going to start up immediately and start writing over our measurements that we had. So with our toggle switch, which we forgot to mention, it's wired. We desoldered an LED off the board, off the balloon sat board, and wired the switch in there as a pull down, so that when it's one way, the data is writing to the EEPROM, but this is all in code that the code's reading pin section. So when it changes over, it won't write data to the EEPROM.
Okay, I understand what you're doing. I wanted to come and look at it.
Okay.
Duh. Yeah, they call us Dr. Love. And we're with McNeese. We did a balloon project to, go up in space to 100,000 feet. I'm Philip Adlesio, the team leader. This is Chad Corbello, who's electrical engineering. This is Terry Stark. She did the programming portion. This is Kalani assisted me with the mechanical, and this is Stephen Bijay, and he is in charge of assisting everything in the group because he is engineering technology, so he kind of covers everything. All right, we decided to make our payload measure UV as a function of altitude. Okay. Now to do this, we had to be able to survive the extreme weather conditions experienced up in the atmosphere, be able to recover our data and analyze it, and also remain within the size and weight constraints set forth by the ACES committee. This is Chad's going to take over with the electrical portion.
Thank you, Philip. These are the ultraviolet radiation sensors. We have UVC, UVB, and UVA. The UVC measures all of UVC nanometers for the wavelength. UVB measures UVB and a part of UVC, and UVA measures all that's required. These are the calculations to select these sensors. This is the spectral energy density function that we use to make sure that our sensors that we chose match the maximum irradiance that we're going to experience for the sun. So what we did is we took the total energy spectral density, and we took the UVC, UVB, and UVA, and we found the ratio for UVA to the total, UVB to the total, and UVC to the total. Then we multiplied that by the total sun flux, which is approximately 14,000 watts per meter squared. Now, doing that, we found that the UVA, UVB, and UVC maximum radiance values are as follows. Now, with the ultraviolet radiation sensors, the relative output is based off the angle of the sun. So for us to find the angle of the sun, we decided to use a GoPro Hero 2 camera to take a picture of a rod that's going to be on a translucent material to where it will be able to cast a shadow. And we're going to be taking pictures of that shadow, and using computer vision, we'll be able to find the angle that's required. But using that angle, we'll be able to find out the exact irradiance values for our sensors. And the camera has a time-lapse mode to where we can take a picture every 10 seconds. And we also have it controlled by the microprocessor to where when we sense our data every 10 seconds, every time we sense our data, this camera will take a photo. And then next we have Stephen Vijay.
Thank you, Chad. This is a schematic of our circuit design. We have our sensors, UVA, UVB, and UVC connected into our ADC through the signal pin. And then right down here we have where we're connected our GoPro camera, where the microcontroller is controlling the GoPro camera. And also we do, as the other team, have a toggle switch to control the read and write functions of the whole process. And then a power switch added also up. In order to figure out the battery selection, we had to design a power budget for the whole payload. After figuring out everything, the milliamp hours that we needed were 217.6. And after doing many different tests through a lot of different batteries, we found that the 2CR5 Energizer battery was the most efficient, and it worked for the best. It is a 6-volt battery, so we will be running 2 batteries in series. We're going to be able to have 1500 milliamps at optimal temperatures of like 70 degrees, but because of that, we realized we had to bring it down to lower temperatures, and we did testing, and we included that all in our FRR report. And the batteries they were sufficient enough and providing our payload with enough power to go through the whole 4-hour. We plan for a 4-hour flight for a safety factor. Next, we'll go to Pawan for introduction for mechanical.
This is about the mechanical requirements. Based on the license constraint, our payload needed to be sustaining extreme temperature of -60 to +60 degrees Celsius, and it needed to house everything, all the materials within the weight budget of 500 grams, and should have sustained 5 meter per second of velocity when it falls down. The materials we used for this payload design was exterior polystyrene, styrofoam, quartz glass plates, and plastic cover. Few of the features about this payload design is we used GoPro camera of dimensions 4.25 by 6 by 3.9 centimeter, and we have a translucent plate above the camera. Also, there will be 2 straws at 17 centimeter space passing through the ropes. This is the mechanical design. We have the one outer box of 2 centimeter of styrofoam, and the other one, the inner, is of 1.5 centimeter, and the dimensions will be 16.4 by 9.7 by 14.4 centimeters. This is one extra layer of, there will be one extra layer of styrofoam protruding out of the outer box where the camera will be placed in between, and it has a height of 9.2 centimeters. Based on all the materials we used, the total weight came out to be 414.8 grams, which is well within the weight limit of license constraints.
Alright, to make sure that everything worked, we of course had to do a couple tests on the mechanical portion. The first thing that I did whenever I was making sure the material we decided to use was appropriate was do some rough hand calculations. Now this right here is the equation for lump sum capacity for unsteady state heat transfer, and this cannot be directly integrated in order to get an exact answer. So what I did was I simplified it to only consider the radiation portion of heat transfer, and this is largely because a lot of these sub-zero temperatures are going to be experienced over there. It's not a lot of wind taking place, so convection won't be a huge factor is what I assume. I came out to around 909 seconds using the volume of our lower portion, which is what will contain the important circuitry. Okay, after this, we then built a test box and put it in a negative 80-degree freezer and saw how long it would take for it to, the internal temperature to lower to 0 degrees Celsius, which is where a lot of our important components will fail. Okay, then the next thing I did was I used AutoCAD CFD to simulate the heat transfer to further validate our theories that this would work. Okay, right here I had to make a volume with boundary conditions that would be of the negative 80-degree freezer first to let it coincide with our actual physical tests. And once it did, I put it in negative 60 degrees and found that it ran for 1,174 seconds, which is an appropriate time to survive the journey. The next thing we had to do was make sure that none of our components would fail in the vacuum test. Nothing would pop, or the glue in the bubbles, because we used Gorilla Glue, would pop. This was done with 10mm HG vacuum, and it went down to also an equivalent of 1.33 kPa, which is below what we will be experiencing up in the atmosphere. And there was no apparent damage to the box. Then the next thing we did was we put an accelerometer inside of our box, and we dropped it from the appropriate height to reach 5 meters per second. From this, we reached a impact of approximately 52 Gs, which is within the limit to survive the shock. Okay, the final thing we had to test was the MATLAB computer vision to make sure that it would be able to measure our shadows adequately. Okay, in this test I used at my house, we set up the camera at the same distance it's going to be from the viewplate, and then shine some lights on a small rod separated by a spring to break up the two shadows, and we found an error of only 3.2%, which is 1.72 degrees off approximately over the couple times we tested it. Okay, now I'm going to switch over to Terry. She's going to explain the software portion.
Okay, so first I decided to determine my sampling rate. Since our camera will be taking a picture every 10 seconds, we decided to go with that, but we found that we could actually go with as low as a 3.5 before we would run out of memory. We're using a 32 kilobyte EEPROM, so the maximum possible samples we can take is 4,096, and we use that over a 4-hour period, and we're going to be taking 1,440 samples altogether, which will total up to, I think that's supposed to be 11,520, but it went away.
Okay, you got about 5 minutes left.
Okay, so here's the algorithm that we designed for a flight program. We're going to start with initializing the variables and the constants in the pin, and we have a main loop, and since we have a switch that will determine if you're in write mode or read mode, if the pin is high, which is a 1, it will read the data from the EEPROM. We're going to save that for the end after we retrieve the payload from the flight. During the write mode, we will be getting our time from the clock. We'll be getting the data from the channels 0 through 2 of our ADC, and we'll be writing each data to EEPROM on each iteration, and we will pause and wait for a 10-second loop. During the analysis program, I'm going to use a program in MATLAB and interpolate the UV over time, and then I'm also going to interpolate the altitude over time, and it will parametrically graph those two together to graph UV over altitude. We have to first get the decimal or the voltage from the ADC, and we'll use that with the decimal value that we get, and we use to find the irradiance for each UV, we have a formula that we will be using with the voltage to determine our irradiance for each one. Any questions?
Okay. Okay, so this is a question for both McNeese groups. So you got this switch in there.
Yes,
right?
Yes.
So we launch, we fly, we land in a tree, we recover. You get your payload. What are you going to do once you get your payload in your hands?
You basically switch the switch from a 0 to a 1, and that way whenever you automatically power up the board, it automatically goes into our serial port communication with our computer to deliver the data to a text file.
Okay. So tomorrow we will probably be, we've got to try to avoid it, but we'll probably be a recovery from hell. So a recovery from hell means that we launch at 6 a.m. and we don't recover until 6 p.m. So what's going to happen to your battery by the time you get to your payload? Okay.
But this switch is just so we don't rewrite over our data once we repower it on if we do. Exactly. So if we attach new batteries to the switch into read mode, then we won't have to worry about it retaking in data.
So the first thing you're going to do is that you're going to switch your switch when you get your hands on your payload.
And even if the battery dies, I mean, the data is saved on the EEPROM, so it's not right.
But if you don't switch that switch, and if you power up, you've lost all of your flight data. Is that correct?
It will not. You'll only lose the samples that you take in the time period that it takes that you turn it on. It'll still have all the other values in the E.
And how will you access the rest of that EEPROM?
You can.
The reading program can access all the EEPROM. What he's saying is, if we were to hook up new batteries and restart it in the in-flight program, well, it's going to write over as far as it takes until we
You timestamp all your data records?
All of it's timestamped.
Yes,
We'll make a big mental note to
the data starts.
It starts
at memory point 0.
So.
Okay. Anything else?
Are those, is that high or read? High or
High, read is high and write is low.
You're reading your pictures into the GoPro memory?
Yes, sir. There's an SD card in there.
The 32 gigabytes. How do you keep them synced with the data in the EEPROM?
It also has a
There's a breakout board that we have that extends the pins on the back of the GoPro, and it helps the remote access from a signal from our basic stand.
When we flip on our program, it will activate the camera and they'll start at the same time and they'll both be on the